Welcome to lecture 14 of the CS4423 networks. My name is Götz Pfeiffer, and this video is about the structure of the World Wide Web and directed graphs. Usually this lecture would have taken place around the end of March, where the World Wide Web celebrates its birthday. It's 32nd by now, and there's a link to an article describing the current state, issues, and other links. So, as a network, the World Wide Web certainly is something that's familiar to all of us because we're using it on a daily basis. As a network, it's different from most of the networks we've discussed so far, which were around people and opportunities for interactions, and as graphs, they were undirected graphs. The World Wide Web is an example of a different kind. It's an example of an information network where the links tend to be directed. Information networks, in general, they're networks that relate pieces of information to each other, documents, parts of documents, through links that represent references of some kind. And by their very nature, in contrast to social interactions, which are typically symmetric, the references only go one way. They point in one direction, sometimes with an underlying time axis even. So the underlying graph of an information network tends to be a directed network. We have seen examples of information networks, and they have existed before the internet. Academic publications, as we have studied them on the Maths SciNet in one of the practicals, they always had a tradition of referencing prior work. That's part of the work ethics, to reference all the knowledge that you're building on, and you do this through references to prior publications. And this establishes a network of academic publications pointing to each other through these references. In addition to the relationship between co-authors that we studied, which is of a more social kind, of a more undirected nature. Now, these days, a large part of this references network is captured on the Maths SciNet and therefore can be processed electronically. And while we're talking about mathematics, mathematical proofs, in a way, form a network of theorems pointing back to theorems that have already been proved. Mathematical theories as complex systems of logically derived truths, one from another, can be described in the form of a directed network, although they're not usually described in this way explicitly. Much of this is only implicit or not mentioned, but in a way, as a point of view, they are complex networks. In a similar way, like computer programs using subroutines or other functions defined earlier to do their work. They form networks of subroutines. Technical documentation of complex systems like computer software, they used to occupy meters of shelves in offices in the 20th century, and nobody would read it because it was so complex, and that was one of the main motivating factors, I think, for inventing the World Wide Web at the time, to put technical documentation onto a computer in a form that all these cross-references can be followed in a convenient fashion. And the way this was done there was through hypertext. invented at the particle accelerator at CERN in the 1990s or a bit earlier. This was about technical documentation in the form of pages, web pages then, and they were defined then in a way that anyone can contribute to this collection of web pages and make them publicly accessible on their networked computer. And there's a piece of software, a so-called web browser, that can retrieve those web pages, those information pieces from those public spaces, and through them being available on the computer, through the links, the hyperlinks and mouse clicks, the relations, the references are easy to process. They're easier to, in a traditional format, you would read a reference to a different academic piece of work at the end of the paper you were studying. Then you would walk back to the library and try and find that piece of work, which of course takes much more time. I don't want to really go into the details of the hypertext, how it's done, how it's organized, but just to emphasize again, hypertext links are one-way relationships. They point from a source to a target. They point from one document that contains the links to the documents that are being referenced. And so through this mechanism, it creates a network of directed edges between documents. There are and there have traditionally been many other ways to organize information. You can do it alphabetically, like the telephone book, or hierarchically, like the folders in the file system on a computer. And there are advantages and disadvantages to all these ways. There are physical constraints that have to be respected. The fact that books need to be stored on shelves, or that the pages in a book come one after another, and there are certain physical restraints that are no longer present when you have your documents on a computer. The hypertext way of linking documents to each other makes the logical relationships between texts, or even within texts, very explicit first-class objects. And through the browser you can click with your mouse on them. The links are immediately actionable. And that was maybe the big change, the new thing at the time. It wasn't that new. There are, at least in theory, predecessors of the World Wide Web, dating back to 1945 in the case of the Memex of Vannevar Bosch, or 1965 the Xanadu project by Ted Nelson, both of which are linked here, and they have their own Wikipedia pages and stories to tell. There are subtleties. I think these days there are more subtleties with different kinds of links on the World Wide Web, which are actually important for the network considerations. Which network considerations? We leave these details outside. What I'd like to discuss now is directed graphs, or how the properties we studied before in undirected graphs are reflected in directed graphs. And there are some similarities, some things are different, some things are subtly different. And one question that the answer to which needs to be refined is the reachability question. Which nodes can be reached from a given node in a directed network? As in, starting at a web page, Where can you get to by just clicking through the links on the web pages that you reach. So there we go, back to the theoretical side. Directed graph is a pair X, or a vertex set X and an edge set E, and now this time the edges are directed edges. That means they are proper pairs, an X and a Y, where X is first and Y is second. So the edge set here is a subset of the direct product, of the Cartesian product of X with itself, the set of pairs of elements in X. And we read this as an edge that points from the first entry to the second. X points to Y. This is no longer a symmetric relationship. The edges point in one direction. Then a path, there's still a notion of paths in such a directed network. It's still a sequence of nodes which are connected by edges, but it's an edge pointing all the way in one direction. It's an edge from xi minus 1 to xi for I from 1 to L. Same as before, that number L, the number of edges being used, is the length of the path. And we might want to write such a squiggly arrow from X to Y to indicate that there exists a directed path, possibly of length 0, from X to Y in the directed graph G. One way to relate directed graphs to undirected graphs is by simply ignoring the direction. Whenever you see an edge, you regard it as a two-way connection between things. And if you do that, then what we used to call connected components become the weakly connected components of the directed graph. Or a directed graph is said to be weakly connected if, when you consider it as an undirected graph, there is an undirected path between all its edges. It's connected between all its vertices, or any pair of vertices. Then it's connected as an undirected graph. And the weakly connected components of G are the connected components when considered as an undirected graph. But then we have a stronger notion of connectivity in a directed graph, namely that of strong connectivity, where we consider a graph strongly connected if between any pair of vertices X and Y there is a directed path from X to Y, that is, X is squiggly pointing at Y in the above sense. This leads to the notion of strongly connected components. These are components, these are subsets of the vertex set, which are firstly strongly connected and secondly not part of a larger strongly connected component of X. In general, a directed graph decomposes as a partition of weakly connected components, and each weakly connected component in turn is a partition of the component into strongly connected components. I want to illustrate this a bit more first in the language of relations that we've used before for undirected graphs. So when we regard a directed graph as a relation on the vertex set X, then strongly connected components can be described as equivalence classes of a certain equivalence relation that can be described as follows. First of all, we notice that in the language of relations, this squiggly arrow relation, the relation that says there is a directed path from x to y, can be described as the reflexive and transitive closure of the directed edge relation, which is essentially the graph, x pointing to y. Now that's the graph regarded as a relation. If you allow longer paths or paths of length 0, then that's constructing the reflexive and transitive closure of this relation. So this new relation, the squiggly arrow relation, then by construction is reflexive. Every point is squiggly arrow related to itself through a directed path of length 0, and it's transitive. As before, you can, if you have a directed path from x to y and a directed path from y to z, then you can simply join the two up to obtain a directed path that leads all the way from x to z. So this reflexive and transitive closure construction gives us a reflexive and transitive relation. It might not be antisymmetric. It might not be there might be pairs of vertices x and y which are squiggly related in both ways, where you have a directed path from x to y and a directed path from y to x. So we can define another relation. I use a general equivalence or congruence symbol and say that x is equivalent to y if this is the case. If there is a path leading from x to y and at the same time a directed path leading from y to x. This is presumably using different edges, different directed edges. You might imagine this as a cycle, where one way around the cycle you travel from x to y, and then further on the cycle you travel back from y to x. This new relation, defined as there's a path from x to y and there's a direct path from y to x, is an equivalence relation. So it's reflexive, symmetric, and transitive by definition. And its equivalence classes are the strongly connected components of the directed graph G. So let's denote these strongly connected components by x in square brackets. X in square brackets is the strongly connected component of the vertex x. Then, since we're coming from the big directed graph, there's now on the set of these equivalence relations another relation, a partial order relation, which I just denote by less than or equals. That's a relation which is reflexive, transitive, and antisymmetric. We've made it antisymmetric by introducing this equivalence. And it's defined as a relation on the set of equivalence relations where the class of x, say, precedes the class of y if there's a directed path from x to y. And I want to illustrate this in an example now. So this partial order relation on the set of strongly connected components of a directed graph leads to what has been called the bow tie structure of the World Wide Web, or indeed the bow tie structure of any directed graph with one strongly connected component that dominates the rest, one that serves as the giant component. So now we've seen this before in random graphs. If you have sufficiently many edges, then a random graph tends to have one connected component that dominates everything else. And similar to this in a directed graph, if there are sufficiently many edges, then one of the strongly connected components is a giant in the sense that it's much bigger than all the other strongly connected components. So there's one big, strong connected component sitting in the middle of the graph, and relative to this strong component, now this is a directed thing, as you see with the arrows here. This is something that's not that you cannot talk about in the undirected graph. Relative to this giant component, you can subdivide the rest of the graph into four more sets of components, strongly connected components. There is, for example, here in green, the upstream components. That's the set of all strongly connected components which have the property that they precede the giant. There is a path from the green area here into the giant, but no path back out, because then they would be strongly connected to what's in the giant already. Similarly, on the other side, there's the downstream components, all the nodes that sit in strongly connected components that you can reach from the giant component. But you can't go back into the giant component from there. These are the downstream component, the out part of the directed graph. And then relative to that, there's a few lost or halfway lost nodes or strongly connected components. They're called tendrils and tubes. Tendrils, these are nodes or components which contain nodes that can be reached from the in part, but from there you can't reach the giant or the out part. Or similarly, these are components from where you can reach the out part, but you can't go back from the out part to there. Or a tube then is an example, or a tube is strongly connected components which maybe line up to provide a path from the in part directly to the out part without being related to the giant component in the middle. And then there are the disconnected components which have no path interaction with any of these. So and this is a picture that you get for any directed graph with a distinguished, strongly connected component, and the weakly connected component that contains the giant strong component necessarily has this global bow tie structure, as it's called. Also, here's an example. Say these are a couple of web pages relating to a local university where a university advertises its classes, its courses, or the networks class in particular, and they in one of the lecture notes they mention a list of college rankings maybe, and the college rankings they mention featured colleges, one of which is NUIG. So you get this cycle here, which in effect puts all the nodes that are concerned here into one strongly connected component. And in this picture, this is the big component, so that makes it the giant. And there you have parts of this small web pointing into the giant, but the giant doesn't point back. And then there are other parts being pointed at by the giant, but they don't point back into the giant. So that's in green, or shades of green, the in part here, and in shades of blue, the out part. And this gray thing here, pointing away from a student's personal page, is an example of a tendril. And that's this description of the World Wide Web goes back to the end of the last century, where the large giant consisted of approximately 1/3 of the vertex set on the web. The three parts in, out, and the tendrils and tubes then roughly have the same size. There are reasons to believe that this is essentially still the same, although the nature of the World Wide Web has changed through social media and different types of links and documents which are more volatile than the static nature at the time. But still, this is one way to describe directed networks and to distribute meaning and importance between the nodes that make up a directed network. I'd like to use the computing facilities that we have in this page to illustrate these concepts in random examples. So starting with a reasonably large random directed graph using the Erdős-Renyi construction, and now asking the networks package to make this a directed graph. I'm passing the directed keyword as true to the constructor. I hope to get one with a giant component. Let's see. I think I won't dwell much on the details. What we'll see here again is breadth first search to answer reachability questions, and depth first search also later. So in a directed graph, the neighbors of a node X are either before or after. A node X has neighbors that point at it, and it has neighbors that it points at. So there's a distinction between successors of X, the nodes that X points at, and predecessors, the nodes that point at X. Weakly connected components then can be computed as before by simply ignoring the distinction between successors and predecessors, and thereby effectively treating the graph as a directed graph. So this weak component program is essentially breadth first search as we had it before on an undirected graph, where we use a queue here, a simple list, loop over the queue, mark the present node as seen, and then find all the neighbors, the successors and predecessors of that node, check whether we've seen them before, and if not, we add it to the list. And we keep a list of nodes here, which eventually, a set of nodes which eventually will be the weak component, and this set of nodes then is returned as the weak component. The list of all weakly connected components then can be found by looping over all the nodes and determining the weak component of every individual node, if that node hasn't been marked as seen yet. And then we can then we get a list of such sets of nodes, each set being a weak component, and we can sort these weak components by length. So if we apply this to the random graph I constructed earlier. We get 11 weak components, and the lengths of these components are 87, that's a big one, and then a few small ones and lots of singletons. Okay. Strongly connected components are best found by a clever depth-first search. Again, I don't want to go into the details. Tarjan's algorithm, which does this in a clever way, is linked here. It has its own Wikipedia page, which is linked here, if you're interested in the details. Now here's an implementation of Tarjan's algorithm, which uses depth-first search. Depth-first search implicitly uses the stack, the function execution stack of the Python interpreter. The algorithm itself uses an additional stack on top of that, and it enumerates as an index all the nodes that it meets on the way consecutively. So as I said, the details of this algorithm are in the web page. It's depth first search rather than breadth first search. This is the recursive part where the stack, the list of strong connected components, the current index and the node are passed as arguments. And here what recursive means, that here in the middle the function calls itself again to construct the strong connected component of a given node X. And similar as for the weak components, to find all the strong components, we loop over all the nodes in the graph, and if the node hasn't been seen, if it hasn't received an index in this case, we construct its strongly connected component and add it to the list. And then all these, some of this is stored as attributes of the nodes in the graph object, which might be in the way if this procedure is repeated. So it's advisable to clean up all these helper attributes that were used as part of the algorithm. And if we run the algorithm on the example random graph, we get strong components, one of size 24, and loads of singletons. So the first one here, the 24 strong component, would be the giant, obviously. Then, in order to determine the out components and the in components, we do breadth first search again. These are reachability questions. The out component first, that's the question, what can be reached from the giant? So for this, we pick a random representative of the giant, call it rep, and then apply breadth first search to this representative to determine all the nodes that can be reached from this representative of the giant component. This will include the giant component itself. But it's breadth first search as we know it, and here it's the successors of a node that are considered, that qualify as its neighbors in this search. So we get a list of nodes back, which here has 49 elements, and this contains the giant and the out component. We can do a similar thing for the in component, using a variant of breadth first search that now considers predecessors of the node as its neighbors. I call this function inReach. I call it in with two n's because in with one n is a keyword in the Python language, and that's better avoid it as a variable name. So if I call this inReach, if this function inReach, then I can assign the result of it to a variable in with two n's, but it stands for the capital N component in the bow tie diagram, and this gives 46 nodes. And this is the giant and the in component. So we've seen the giant now as part of the in component and the out component, so we can compute it again as the intersection. This ampersand is set intersection in Python of the two lists of nodes. And then I want to distinguish this from the tendrils and tubes, I want to call the union, this symbol is set union in Python, the union of in and out as the core of the graph. And this gives me 71 nodes. That's now the giant, the in component, and the out component. Okay, so to separate things properly, I remove the giant from in and out, and then I've separated the core of 71 vertices in this example into the giant, consisting of 24, the in component of 22, and the out component of 25. Now, this is where the fun starts. I mean, fun means it's breadth first search again, and to find the tubes and tendrils where. So we've now determined the green, the red, and the blue part of this picture, and we've called this the core of the graph, and the gray part here then is the rest. And as it stands, the gray part is pointing away from the core or pointing into the core, and the core is basically pointing at itself. If you stare at this picture for long enough, you might believe me that, where are we here? We can find the tubes and tendrils by applying breadth first search again to the graph, to the representative of the giant component, by reversing all the arrows, all the edges in the graph, but have both their endpoints in the core component. Now think about this for a moment or afterwards. We reverse all the edges in the graph that have both their endpoints in the core component. So we'll do this in a copy H of graph. So I collect all the edges that are to be reversed in a list flip. That's all the edges in the graph which have the property that, considered as a set, it's a subset of the core of the graph. It says there's 92 of them, that's a lot, and then I flip them. So for each edge in this list, I remove this edge from the H copy of the original graph G, and then I add to the H graph the edge in reverse order, E of 1, E of 0, the flipped edge. And then I apply the procedures again, outreach, apply to the representative of the giant in the new graph, finds a set of nodes called out2. If we remove the core from that, out2 sits outside the core. Similarly, inReach with two n's, wasn't it? inReach with two n's finds a set in 2 where the core is removed from the result. The intersection of those two sets then is the tubes, and removing the tube from the rest leaves two sets of nodes in tendrils. That's, yeah, think about it or try this in other examples. So here we get, in fact, non-empty sets, 4 in tube 2, 6 in 2, and 3 in out 2. Now here it says if tube 2 ends up being empty, then the example was not interesting from the start, so go back and start over. But this is apparently interesting enough. So we have 4 vertices in the tube 2 set, and now we can set about drawing this particular graph in a bow tie fashion, which requires some work, because different parts of the graph have to be drawn at different times with different colors in different portions of the overall diagram. Again, I won't go through all the details, but here's how it's done. I define a new graph which consists of the subgraph of G of what we call the core and the core 2. Then I use the spring layout function to compute layouts for the individual portions of this graph, in 1 in 2, out 1, out 2, and tube 2, and distribute them across the page. And so that's computing positions for the nodes in these graphs, separated by their function in the bow tie structure. And then using these positions, I draw the portions of the graph bit by bit in different colors in their positions, and with colored edges between them to tell them apart. And it gives a graph like this, where we have, okay, these are different colors. So we have in red here the giant. So the red part here is the giant. The yellow part is the in component. And if you look at this closely, all the yellow nodes point to the giant, and some of them point to themselves. And the purple part here is the out component. And then there's a few tendrils, as they're called, and I think there's, in fact, here starting at vertex 4, 23, 55, there is in fact a gray thing leading around the giant component, verifying this bow tie constructor on this random graph. Other random graphs end up differently. So yeah, I skipped over a lot of details here. You might want to try this for yourself with different random graphs, and working through the individual commands bit by bit. If there are questions, let me know. For now, I'll stop this here.